So another types of two-dimensional defects that are related to surfaces are called stacking faults. And I will just give you one particular example of how stacking faults can be made in a material. So if you think about close-packed plane of materials or of atoms, so they will have these particular configurations, right? So atoms will be closely packed. And in this particular case, you can recognize different parts or different points in this first layer, which are labeled with A, B, and C, in which the atoms from the second layer can find their position. So what you're doing is that you're growing, for example, the material, and you're stacking atoms on the top of each other. So first you form one layer, which will form this closed, dense packing structure. And then you're asking a question where the second layer will be, whether the atoms from the second layer will simply sit on the top of the first atoms, whether they will take the position B or C, etc. And there is the major distinction between two classes of materials, which are FCC, in which the stacking is ABC, ABC, ABC. What that means is that first layer of the atoms will take the positions A. Then the second layer will take the position B. So the red circles here is the second layer of the atoms. They're taking the position B. And in the case of the FCC materials, the third layer then will take the position C. So the third layer here will be C. In contrast, hexagonal close-packed HCP crystals form the AB, AB, etc. structure. What that means is that you have the first layer of the atoms, the second layer of the atoms will take position B, the third layer will take again position A, etc. So what that means is that the difference between FCC and hexagonal close-packed structure is simply in the way of stacking of individual layers that have identical structures, right? So you start from closely dense packed layer, and the only difference is how you stack them on top of each other, and you will form either FCC or hexagonal type of a structure. And this is just from the cross-section. This would be FCC and hexagonal close-packed structure. Again, different colors here represent different layers of the atoms. So what is a stacking fault, and why do we talk about stacking? So the stacking faults, the name itself tells you, is that there is a fault in stacking. So what that means is that, for example, you can have an FCC crystal, and for some reason, instead of having ABC, ABC stacking, like in the rest of the bulk, in certain specific localized regions, you will have stackings AB, AB, etc. What that means is that you have an FCC crystal, and very locally, you have hexagonally packed structure. So it simply means that there is a localized defect in the packing itself. So by the definition, then, the stacking fault will be an interface in which one part is displaced by a vector that is not, so this not is important, a translational symmetry vector. What that means in this particular case that I just explained is that the translational symmetry vector in the FCC crystal would be between blue atoms, for example. So it would be 3 layers. So the stacking repeats itself after 3 layers. So if you have some kind of stacking that disturbs that particular packing, then this would be called a stacking fault, meaning that the translation or the mismatch does not necessarily follow it does not follow the translational vector itself. So I will give you a couple of examples just to demonstrate how this can be formed, and in which instances this can be formed, and when stacking faults, how they are described, how they are introduced in the material, etc. So this would be, again, just a cross-section of a material. In this particular case, it is a FCC crystal. So again, different colors represent different stackings or different positions. And this is FCC because the stacking is ABC, ABC, etc. So this would be the perfect crystal, right? At the top. And at the bottom, there is the stacking fault. And how do we know that? Is that, for example, here, we see there is the layer A, there is the layer B, there is layer A, B, C, etc. So very locally, the stacking sequence of an FCC crystal is perturbed. So this would be, for example, a stacking fault. And in this particular material, it can be, for example, formed by vacancy diffusion. So if you have a material that has high density of vacancies, if you introduce processing, for example, by changing the temperature of the material, and if these vacancies diffuse throughout the material, they can form these stacking faults. This is one mechanism of formation. What is really important to notice here is that locally you do have a stacking fault which is within the bulk of the material, but then it has to be surrounded or it has to be edged with an edge dislocation. So one thing that you will notice, that on the left-hand side, the stacking fault does not exist, right? On the right-hand side, the stacking fault is here, but then everything is, so this region here ends up with an edge dislocation. And it turns out that these edge dislocations that are connected and related to stacking faults are called partial dislocations. So the reason why it's called partial dislocation, again, is because the Burger's vector itself is not a vector of the lattice itself. So it's a portion of or it's a part, or it's a segment of a lattice vector within the crystal. So, and why do they form? So previously we mentioned that from the energy perspective, the dislocations carry an elastic energy that is proportional to the B squared, to the Burger's vector squared. And we mentioned that perfect dislocations in materials, for example, in the case of FCC crystals, this would be a Burger's vector from a perfect dislocation. This dislocation can segregate into two dislocations if their elastic energy is lower than the elastic energy of the initial dislocation itself, right? So what is illustrated here is that, for example, in this particular case, this would be the Burger's vector in FCC crystal, and it can separate, or it can be, it can form two so-called partial dislocations with Burger's vectors B1 and B2, and they're schematically illustrated here. And maybe this image is kind of difficult to understand, but let me try to explain you. So this is the first stacking layer, A. This will be the second layer, B, and this region here is the core of the dislocation, or this is, you can imagine that there is one missing plane because there is one extra plane coming from beneath. And there is this region of the material where there is the expansion and the atoms are further apart from the ideal position. So if you separate this dislocation into two partial dislocations, they will form again the dislocations with smaller Burger's vectors, and therefore this distance between these two atoms will be smaller. So there are two things that need to be satisfied. So first, B1 plus B2 has to be equal to B. So their magnitude, the total Burger's vector has to be satisfied. So, and we can see that, for example, the Burger's vector A2, 1 bar 1, 0 is equal to A6, 1 bar 2, 1 bar plus A6, 2 bar 1, 1. Okay, so if you do the math, you can see that this is, the Burger's vector is preserved. This is energetically favorable because B squared is larger than B1 squared plus B2 squared. In other words, the elastic energy that is contained or that is formed by formation of two dislocations B1 and B2 is smaller than the elastic energy from first initial dislocation with the Burger's vector B. So this is energetically favorable. However, this particular displacement of the atoms, again, these are called partial dislocations because, again, this is not a translational vector within the crystal. And as a consequence, in between these partial dislocations, the stacking faults are formed. Okay? So sometimes it might be a little bit difficult to visualize this. At the moment, what I would just like to mention and what you should probably try to remember and understand is that if you do have formation of the partial dislocations, they usually end connected with the formation of the stacking faults, right? So if this process happens, as a consequence of this process, the stacking faults will be formed. And this can be very often seen in the material. It's a very common process. In the metals, the stacking faults are so common, very, very common. And this would be a transmission electron micrograph of a situation or where, so this is a TM image, where these lines here are stacking faults. So these parallel lines are just stacking faults that are present in this material. And if you look more closely, you will see that they are separated, or at the edges of these regions that contain the stacking faults, there are individual partial dislocations. So these would be dislocations. Okay. So again, you have partial dislocations that are produced in one way or the other, and in between of that, these two pairs of partial dislocations, you will form stacking faults. Again, very, very common types of defects that sometimes have certain benefits, sometimes we want to avoid them from the material.